Good morning, student. In the last part of the video, we have discussed about the superposition of two simple harmonic motion with different phases and amplitude traveling in the same direction. In this part, we are going to discuss superposition of two simple harmonic motion with different frequency. In the last part, the frequency of the two simple harmonic motions were similar, but in this case, we are considering two simple harmonic motion with different frequency. Okay. Suppose we consider two harmonic oscillation. X1 is equal to A cos omega 1 into t plus phi 1. Okay, and X2 is equal to A cos omega 2 into t plus phi 2. Okay, and this quantity is known as the phase factor. Phase factor. Now the phase difference between these two simple harmonic oscillation can be computed as delta is equal to omega 1 into t plus phi 1 minus omega 2 into t plus phi 2. So it will be omega 1 minus omega 2 into t plus phi 1 minus phi 2. This is the phase difference between the two simple harmonic oscillation. But in this expression, one can see only this factor depends on time. Other factor is constant in time. So this factor is not important, because in simple harmonic oscillation, everything should changes with time. If something doesn't change with time, that means its role in simple harmonic motion is not important. Therefore, from the preceding discussion, we are going to neglect this term. Okay, so we can write as two simple harmonic motion as x1 is equal to A cos omega 1 into t and x2 is equal to A cos omega 2 into t. Now what we have to do, we have to superimpose these two oscillation. Okay, thus we have to adapt these two terms so that we get the resultant oscillation just like in the previous case. So let x be the resultant oscillation, then x will be equal to x1 plus x2. So we can write A cos omega 1 into t plus A cos omega 2 into t. So A we can take common, cos omega 1 into t plus cos omega 2 into t. Okay, this is, we have to apply the formula. Here we have to apply the formula cos A plus cos B. So if we express it, it will be of the form 2A cos omega 1 minus omega 2 divided by 2 into t into cos 2 omega 1 plus omega 2 into t. Okay, so you can see there exists two oscillating term here. So next what we can what we'll do in the derivation, that we'll take we'll give some name of these two term, omega 1 plus omega 2 divided by 2 and omega 1 minus omega 2 divided by 2. We'll give some name to this term so that you can understand its behavior properly. Okay, so let's say omega average is equal to 2 divided by omega 1 plus omega 2. Okay, omega 1 plus omega 2 we have denoted this as omega average because this is omega 1 plus omega 2 divided by 2. And next term omega 1 minus omega 2, let's say it omega modulated. Okay, so it will be 2 omega 1 minus omega 2. Okay, omega 1 plus omega 2 divided by 2, we have taken it as omega average. Omega 1 minus omega 2 divided by 2, we have taken it as omega modulated. Okay, now we are going to put these two things in this expression. So this is expression 1. Just substitute the value of omega 1 plus omega 2 divided by 2 and omega 1 minus omega 2 divided by 2 in this expression. So what we will get, x is equal to twice a cos omega modulation into t into cos omega average into t. Okay, now this term will put as resultant amplitude. Okay, say this term is a here will be a function of time, because this function is oscillating with time. Therefore, a resultant amplitude x is equal to at cos omega average into t. Okay, so the difference between this oscillation and the resultant oscillation in other cases is that in other cases x is equal to usually what we write cos omega t plus phi, right? So in this case the amplitude a is not a function of time itself, it's a constant, but it is modulated by this factor. So this factor will determine the value of the whole resultant oscillation. But in this case there are two time dependent factors. One is amplitude itself is a function of time, and there will be also a resultant phase factor for this wave. So when two waves of different frequency superimpose in the resultant amplitude, we get amplitude is also time modulated, and there will be always always the existence of the phase factor. Okay, so now we are going to plot each of this function individually. Okay, so you see omega modulation is equal to how much? Omega 1 minus omega 2 divided by 2. On the other hand, omega average is equal to 2 divided by omega 1 plus omega 2. So you see omega 1 minus omega 2 divided by 2, its value is lesser than omega 1 plus omega 2 divided by 2. Therefore, time period for t modulation will be greater than the time period of t average. Therefore, t modulation average is greater than t average. Okay, so therefore if we plot these two functions in a single plot, then it will be something like that. Okay, this is the factor omega, and this is the amplitude at. Because amplitude at is a function of how much? Twice a cos omega modulation into t. Omega modulation, it has higher time period, therefore I have plotted like that. And omega average, the time period for such oscillation will be lesser than the time period of t modulation. Therefore, we can put those oscillations inside this envelope. It will be like this. Okay, so this is 80 and this term is cos omega average into t. Okay, and this term is 80 is equal to twice a cos omega modulation into t. Okay, so when two waves of different frequency superimpose, the resultant amplitude will be of this form. There will be a bigger envelope, and in that bigger envelope there will be many other small oscillation. The small oscillation is given by this part cos omega average into t, and the envelope which means the amplitude of the resultant wave actually is determined by this factor at is equal to twice a cos omega modulation into t.